Hello, my name is Anthony Hank.
I'm Michael Krasik.
I'm Mary Lou Ross.
I'm Solomon Sakib, and our presentation is on scaffolding for central nervous system regeneration.
The central nervous system is quite literally the backbone of basic human biological function. And with recent trends coming out that highlight the ALS challenge, Parkinson's disease, and other spinal cord injuries, we feel like treating these complications in the central nervous system is a matter of global importance. And this is because these injuries can be debilitating and permanent, and this is due to the fact that nerve regeneration in the central nervous system is very poor. The audience for such product would be manufacturers who would produce it, the researchers and doctors who will be handling these firsthand, and patients with nerve damage who will be benefiting from it the most.
So our approach to this need will be through the implantation of a hydrogel scaffold, which will provide a combination treatment through the combination of cellular delivery and drug delivery. Through this, we would hope to induce the generation of new neurons as well as the repair of existing damaged axons. The hydrogel itself will act as a physical scaffold onto which neural stem cells will be seeded onto, and we would hope through the incorporation of growth factors we'd be able to control their differentiation into either neurons or oligodendrocytes. We would also incorporate various peptides in order to mimic the natural neural electrocellular matrix, thereby helping to enhance cellular adhesion, survival, as well as the interactions between the biomaterial itself and the cells. The second aspect of our approach will be a drug delivery system where we hope to deliver biologics such as neurotrophic factors and platelet-derived growth factors, all of which have been found to contribute to the growth and differentiation of neurons and their axons. The utilization of a hydrogel will provide a localized, directed approach of drug delivery, which will help to circumvent the limitations typically involved in other conventional systems due to the fact that diffusion between the blood and spinal cord is very limited. We would hope that to utilize a nanoparticle drug delivery system in which polymeric nanoparticles will encapsulate the growth factors, and once released from the hydrogel will provide a sustained and prolonged delivery.
So from a cost-benefit standpoint, our solution actually carries a lot of the same costs as the original or on-the-market solutions that you may be familiar with. Firstly, surgery and a lot of upfront costs associated with it. You have the potential risk of surgery in order to assess the situation or the extent of the disease, and obviously any painkillers associated with that or any drugs that are required during the trial. However, where our device really benefits from is that it restores nervous function as opposed to just treats the issue and mitigates the effects. So therein removing the need for lifelong continuous care, which includes continuous physical therapy appointments, continuous medication, and other services that may rack up a lot of costs throughout the life of a patient. Therein restoring the quality of life of the patient and returning that patient to the state from where before any of these complications arose.
So currently on the market and in clinical trials, there are treatment options for people with spinal cord injuries and neurodegenerative diseases. First, we looked into drugs that slow down the process of neurodegeneration and that try to treat the symptoms of these diseases. There's also options for electrical stimulation devices, such as electrodes. Right now, there are over-the-skin electrodes that are on the market that are available to patients that have been shown to produce a little bit of sensation and function in upper body, but there has been problems trying to do that in the lower body. Long-term implantable devices are still under clinical testing and have shown a little bit of pros in testing. And there's also robot gait training, which helps patients learn how to move more efficiently, for example, out of bed and into chairs. It also helps caregivers in therapeutics. So our scaffold is a much better treatment option than the previous listed because one, there's no need for bulky hardware like the giant exoskeletons and the implantable devices that will be under the skin as we saw in the other treatments. There's also the fact that the scaffold will eventually degrade, so there's no need for a second surgery to remove anything or add anything in. And also once the scaffold degrades, it's like nothing was even there. And lastly, and most importantly, this option gets to the root of the problem, whereas the other treatments only mask the secondary effects or try to treat the aftermath of these problems. And that's why we think that this solution is a much better option.
All right, these are our sources, and thank you for watching.